Alright, so let's talk about a class of equations called autonomous equations. So autonomous equations are special in that they don't really have anything to do with their independent variable, which is usually t. So it's just an equation in terms of y prime and y. They're also called time invariant equations because, like I said, they don't have the time really has no effect on the system that's modeled by autonomous equations. So what do we need to know about autonomous equations? Well, we need to be able to do a couple things. Okay, the list is sort of long, but it's usually going to be the same. You're going to be given an autonomous equation, and then you're going to go through a series of steps that we're about to do, and at the end you're going to end up with a graph of y versus t for a bunch of potential functions. Okay, so the first step is to find what are called constant solutions. The constant solutions are constant, so y prime is 0. Y isn't changing with respect to t. So what we're going to do is sub in 0 for y prime to find out for which y's this we're going to have a constant solution. So I can solve this pretty easily, right? It's just a little bit of algebra. You should be used to this. You used to do this in algebra 2, but y versus t, not y prime versus y. Well, that's just a change in variable name. That's all. So now I know that at y equals 0, 1, and -1, I have constant solutions. Well, I'm also going to find my inflection points, again, not in terms of x or t, but in terms of y. So I'm going to derive y prime to find y double prime. So if you derive this guy with respect to t, you're going to get 3y squared times y prime, a little bit of chain rule, minus y prime. And again, if you're uncomfortable with this, write it in differential notation and it'll make it a little more sense. So I have that. I'm going to find where my inflection points are. I'm going to factor out a y prime, get 3y squared minus 1. So now I can say, well, 3y squared minus 1 equals 0, and y prime equals 0 will give me my inflection points. Well, y prime equals 0, I already did it. I already found where that happens. And when I have a constant solution, I'm not going to have inflection points. But this guy will give me all the inflection points I need. Y equals plus or minus root 3 if I solve the 3y squared minus 1 equals 0. So that's where my two inflection points are going to happen. So now what I'm going to do is sketch what's called a phase line. A phase line is very simple. It's just a vertical line that runs from y equals negative infinity to y equals positive infinity. And all it does is it shows me where my y is increasing and where it's decreasing. So what I'm going to do is give myself some placeholders and sketch or actually just denote where my constant solutions are. Here it's going to be, let me give myself some more room. I'm going to sort of denote y equals 0, y equals 1, and y equals -1. That are my constant solutions, right? And then I'm going to ask where is y increasing and where is it decreasing. If you're good at sketching functions in your head, you can go ahead and just do it. But if not, what you can do is sketch y prime versus y, not y versus t, but y prime versus y, to figure out where y is, or where y prime is positive, in other words, y is increasing, and where y prime is negative and y is decreasing. So I'm going to go ahead, and I already know that y prime equals some function of y, namely this function, has zeros at y equals 1, y equals 0, y equals minus 1. And again, this may be a little mind-bending, the fact that we're sketching y prime versus y, but it really shouldn't be. If you want, you can replace these with v and t, v and x, whatever variables you want. But the idea is that we're just graphing this in terms of this. Okay? So now, all I'm asking is, when y tends to infinity, what is this function going to do? Well, as y tends to infinity, it's going to be infinity times infinity times infinity, or just infinity. And then when y tends to negative infinity, it's going to be negative infinity times negative infinity times negative infinity, or negative times negative times negative, which is negative. So I'm going to tend to negative infinity. Okay? So now in order to be able to connect these two, I'm going to have to go through my zeros. And since all my zeros are multiplicity of 1, I'm just going to go through them. If I had a zero of multiplicity of 2, so for example, if I had y minus 1 squared, I would approach y equals 1 and then go back, right? Remember how that worked from Algebra 2? So now I got my function. Now I can tell from negative infinity to negative 1, my y prime is negative. So my y is decreasing. So I'm going to denote that with the arrow pointing down on my phase line, okay? And then from negative 1 to 0, my y prime is positive and my y is increasing. So there we go. And from 0 to 1, it's negative decreasing, and 1 to infinity positive increasing, okay? If that confused you a little, go ahead and rewind a minute, make sure you get this. Because our phase line is very important in the next step, which is the final step, actually graphing the function. When we graph the our potential functions, we're usually going to start t from 0 because autonomous functions, autonomous equations, like I said, are time invariant. So we don't really care about. Not only do we not really care about t, we usually just don't. We just altogether forget about time that's before 0. That doesn't really make any sense. So we have y versus t. This is the first time t has entered the equation. Okay, so we're gonna graph our constant functions. Okay, so y equals 1, y equals 0, and y equals negative 1. Then we're going to draw our inflection points, y equals plus or minus root 3. And now I'm going to actually start drawing in potential functions for each region. This is one region, this is one region, one region, one region, one region, one region. Okay, so I'm going to draw 5 or 6 potential functions. So I'm going to start for the region -1 to minus infinity. Here, my phase line tells me that my functions are going to be decreasing. Okay, so I'm going to start at -1 and start decreasing and dozing off. Okay, then I'm going to start from here and ask my phase line, well, are my functions increasing or decreasing? It's going to tell me they're increasing. So I'm going to start at -1. I'm going to start along my constant solution and then start increasing. But then when I reach the inflection point, I'm going to realize something. The rate at which I'm increasing up to this point has been positive, right? I'm increasing like an exponential function. But at this point, it's going to change. So I'm still increasing, but at a decreasing rate, at a negative rate. So I'm going to start increasing at a decreasing rate, and then eventually doze off into or approach this other constant solution. Okay. So I'm going to draw another class of equations, solutions that are going to start after the inflection point. So they're going to start here. Well, they are going to start like this. They're just going to start as they're going to be increasing, but at a decreasing rate, and they're going to approach y equals 0. So let's do between 0 and root 3. Our phase line says it's going to be decreasing, so we're going to start. Well, we can't start here, because if we start here, we're going to be decreasing into another region. So we're going to go up. We're going to start from here. We're going to start decreasing, change of inflection point, change of rate, done. We were increasing at an increasing rate, and now we're decreasing at an increasing rate, and then decreasing at a decreasing rate, and done. We're going to draw another one here that goes like this. Okay? And then we're going to go do one for above y equals 1. Well, here my phase line tells me that it's going to be increasing, so it's just increasing. Done. So now the very, very last part is labeling each of my constant functions as stable, unstable, or semi-stable. Stable is when both stuff below it and stuff above it, functions below it and functions above it, are converging to it. Unstable is when they're diverging from it, and semi-stable is when some are converging, some are diverging. So this one is unstable because nothing is converging to it, everything is diverging from it. This guy is stable, and this guy is unstable. Okay, So there you have it. Autonomous equations, very simple. You just have to sort of wrap your mind around the fact that here a lot of the work that you're going to be doing is in terms of y primes and y's, not y's and t's, except for the very last part where you're going to report back your graph as y versus t. So there you have it.